We will now continue our introduction to organic chemistry by looking further at isomers. You have already seen that there are things called structural isomers, compounds with the same formula but different structures, essentially coincidences. Look further to the compound C2H2Cl2. As you can see, this is a double-bonded carbon with 2 chlorines and 2 hydrogens, which can be drawn in one of 3 different ways. Therefore, there are 3 structural isomers. If one looks at the naming, all 3 compounds have a double-bonded carbon, which makes them ethene. They also have 2 chlorines, which makes each of them dichloroethene. The first compound, with the chlorines on the same side, is 1,1-dichloroethene. The other 2 compounds have chlorines on opposite sides and are therefore 1,2-dichloroethene. As you may recall from your study of coordination compounds, these are geometric isomers, with the cis compound having the chloride ions 90 degrees apart and the trans isomers being 180 degrees apart. For geometric isomers, there are 2 simple questions to ask. First of all, is there a carbon-carbon double bond? If the answer to this is yes, then there may be geometric isomers. Secondly, are there identical groups on opposite sides of this carbon-carbon double bond? If the answer is yes, as in a chlorine on the left and a chlorine on the right, the answer is definitely there are geometric isomers present. We'll conclude our discussion of isomers with a simple question. You now see 2 molecules. Are these 2 molecules identical? They both are tetrahedral carbons. They both have blue, green, yellow, and red attachments to them. However, if you look closely, you will find the answer to the question is no. They are actually not identical to each other. As a matter of fact, they are mirror images. These 2 molecules constitute what are called optical isomers, or, as stated, non-superimposable mirror images of each other. They possess what are called chiral senses, where chira is the Greek word for hand. So you can have a left-handed or a right-handed molecule. If one is looking for a chiral center, there is once again 2 questions that need to be answered. The first, is there an sp3 hybridized carbon, a carbon with 4 single bonds? If the answer to this question is yes, then maybe you have a chiral center. Secondly, are there 4 different groups on that sp3 hybridized carbon? If the answer to this question is yes, then you definitely have a chiral center. There can be more than 1 chiral center in a given molecule. These chiral centers are called optical isomers because they bend polarized light in opposite directions. They are also essential for life. DNA and RNA helixes are handed molecules. They bend either to the left or the right. Enzymes are also handed molecules that allow you to have the lock and key interactions. This is a brief introduction on how to spot chiral senses. You will find when you take organic chemistry that 2 to 3 chapters are dedicated to naming and determining the properties of these unique compounds. We now move on from simple hydrocarbons and the discussion of isomers to oxidized hydrocarbons, carbon molecules that contain carbon, hydrogen, and oxygen. In its most reduced form, you have carbon as diamond, where there are 4 carbon-carbon bonds. Every carbon is attached to another carbon. Moving along, from 4 bonds, you can have 3 carbon-carbon bonds in an alkyne with a triple bond, 2 carbon-carbon bonds in an alkene with a double bond, or single carbon-carbon bonds in an alkane where you have sp3 hybridized carbons. As mentioned, carbon can form 4 bonds. As you know, being in group 6, oxygen can only form 2. So your first oxidized hydrocarbon would have 1 carbon-oxygen bond. You have a carbon with an OH group on it called an alcohol. This is followed by 2 carbon-oxygen bonds in what is called a carbonyl group, or a C double bond O. These can occur in 2 unique different fashions. The carbonyl could be at the end of the chain, or you could have a terminal carbonyl. This is called an aldehyde. The carbonyl could also be someplace in the middle of a chain, where you have a medial carbonyl, which is called a ketone. In this description, the letter R simply represents the remainder of the molecule. After 2 carbon-oxygen bonds would come 3 carbon-oxygen bonds. Since oxygen can only form 2 bonds, you would need a second oxygen. So you get a C double bond O with an OH also attached for 3 carbon-oxygen bonds in what is known as a carboxylic acid. Finally, the most oxidized state of carbon has 4 bonds carbon to oxygen, 2 carbon-oxygen double bonds, and is carbon dioxide. So now moving on to the naming protocols for oxidized hydrocarbons, compounds which contain carbon, hydrogen, and oxygen. As you saw, the first of these are alcohols, where an H is replaced by an OH group on the carbon. To name these, you remove the E at the end of the hydrocarbon name and replace it with the suffix OL. And then the OH group has the lowest possible carbon numbering. So for example, you see a molecule. It is a 7-carbon chain, which would be a heptane. However, an OH group is present, which makes it a heptanol. The OH is closest to the right, so that's where we start counting carbon 1, which makes it a 3-heptanol. And the methyl group winds up on carbon 5, so the compound is 5-methyl 3-heptanol. Another more complex example, you now have 2 features. I start again looking at the longest chain, which is 8 carbons, which would be an octane. However, there is an OH group and a C double bond C present. Each group needs to get a number, with the OH getting the numbering priority. This means I would start counting from the left on carbon 1. So I would have an octenol, where since each group gets a number, the OH is on carbon 2, the double bond starts on carbon 5, so it's an oct5-ene 2-ol, and the chloro group winds up on carbon 7, giving the complete name 7-chloro oct5-ene 2-ol. Continuing with naming oxidized hydrocarbons, we've previously seen how to name an alcohol, where the H is replaced by an OH. We now move on to the next most oxidized type of hydrocarbon, a carbonyl, which contains a C double bond O. As mentioned, there are 2 types of these. In the first case, you can have an aldehyde, where the carbonyl group is terminal or on the end of the chain. In this case, you remove the last E in the name and replace it with AL. aldehyde carbonyls are always carbon number 1. So you see a molecule where you have a 5-carbon chain, which would make it pentane. But there's a C double bond O on the end, which makes it a pentanal. Starting counting from that end, there's a methyl group on carbon 3, which would make the molecule 3-methyl pentanal. Besides being on the end, you could have a ketone, where the carbonyl group is someplace in the middle of the carbon chain. Once again, we remove the last E from the name of the molecule, and this time replace it with O-N-E, pronounced own. The ketone carbonyl is always placed on the lowest possible numbered carbon. So now we see a molecule that is a 7-carbon chain. The medial carbonyl group is closest to the left, where we start counting from carbon 1. This makes it a 2-heptanone. There are 2 methyl groups on carbons 3 and 5. Each should get a number. So the name of the molecule is 3,5-dimethyl 2-heptanone. With oxidized hydrocarbons containing CH and O, we first saw alcohols where an H was replaced by a single bond OH, and carbonyls which contain a C double bond O, which could be either aldehydes or ketones. Lastly, we have carboxylic acids, which have a terminal carboxylate group, a C double bond O, OH. To name these, one removes the last E from the name and replaces it with the phrase oic acid. The carboxylate carbon is always carbon number 1. So if we look, you see a molecule that is a 5-carbon chain, which would be a pentane. It has a terminal carboxylate group, which makes it pentanoic acid. There is also a methyl group on carbon 3, therefore the name of the molecule is 3-methyl pentanoic acid. One should remember there are only 6 strong acids, so carboxylic acids are all weak acids. That means, as acids, they donate H+ and exist in equilibrium with the conjugate weak base, which you see here. The conjugate weak base is called an O8 ion. So our 3-methyl pentanoic acid is in equilibrium with the 3-methyl pentanoate ion. Since all carboxylic acids are weak acids, it would pay to look at the relationship between relative acidity of weak acids and their reactivity. In organic chemistry, the pKa value is used to measure relative acidity. So let's review the fundamentals. Acids, according to Bronsted and Lowry, are proton donors, or according to Lewis, are electron pair acceptors. Weak acids exist in equilibrium in water with the conjugate weak base, HA in equilibrium with H+ plus A-. The behavior of the weak acids is defined by the acid dissociation constant, Ka, products over reactants, the concentration of H+ times the concentration of the conjugate base A- over HA. And acidity is measured by the pH scale, where pH is the negative base 10 log of the hydrogen ion concentration and is the measurement of acidity. As pH decreases, acidity increases. As acidity increases, the value of Ka increases. However, as the value of Ka increases, the value of pKa, the negative base 10 log of Ka, decreases. So as you can see here, for a series of weak acids, HA, HB, HC, and HD. HA is the strongest of the group, so Ka goes down in the series, which means pKa goes up, but reactivity goes down. So pKa and reactivity have an inverse relationship. Also remember, a stronger weak acid will be in equilibrium with a weaker conjugate base. And the acid dissociation Ka plus the base dissociation Kb give the universal constant, the dissociation constant of water, Kw. So if one looks at the conjugate weak bases of our weak acid series, A minus, B minus, C minus, and D minus, since HA had the lowest Ka, it's going to have the highest Kb, which would mean the lowest pKb. A minus would also be the most reactive. So Kb and reactivity have a direct relationship. In addition to oxygen, organic molecules can also contain nitrogen. There are several different classes of molecules that contain nitrogen, but for this introduction, we will simply look at amines. Amines are substituted ammonia molecules. To name them, you name the substituent groups in alphabetical order, and then end with the word amine. So here you see a molecule. It has a 1-carbon side chain, which is called a methyl group, a 2-carbon side chain, called an ethyl group, and a 4-carbon side chain, called a butyl group. However, unlike the ethyl or the methyl, the butyl group has several unique positions where it could attach to the nitrogen. Therefore, the points of attachment must be specified. So this is a 2-butyl group, and the name of the molecule is 2-butyl ethyl methyl amine. A deeper look into the reactivity of amines, which are substituted ammonia molecules and hence weak bases. We see the original ammonia molecule with its unshared pair of electrons. A single substitution, replacing one hydrogen with an organic group, is called a primary amine with 1 degree symbol. 2 substitutions can occur where you have a secondary amine, 2 degrees of substitution, or you could have all 3 hydrogens replaced, have a triple substitution, and have a tertiary amine, or 3 degrees of substitution. These are shown to give an example of something called steric hindrance, or clutter, which affects the reactivity of molecules in organic chemistry. In all 4 types of amines, the lone pair of electrons are the reactive center. As you can see, as more substitutions are added, there is less access to this reactive center. Reactivity therefore decreases with substitution, and this is the meaning of steric hindrance. The more substituted something is, the least reactive it becomes.